Okay, we'll go into um, the next chapter, which is your orientation, tolerances. Okay, so the very first thing you have to know is your symbol. So we have three geometric characteristics. So the very first one is your angularity, and it looks like this. See that little angle-like thing, and then your parallelism is like this, and perpendicularity is like this. We have already done one chapter on the symbols, so you should be able to identify which symbol is what. So if you see the symbol, angularity. When you see the symbol, parallelism. So that's in our test, so previous test. So this one is a perpendicularity. Okay, you gotta give me the right answer. So right now we're getting into orientation, tolerances, so we definitely need to deal with these three major symbols, and these are our geometric characteristics. And these are just the orientation, tolerances zones, major points. But of course, we're gonna get into it one by one. And like I said many times, the slides given to us are pretty bad. So just be patient with it. You can read, each one of them later. It's just like giving you the summarize points. I would do this, by the end of the lecture in the chapter. Go back to here to read these points, and we'll go straight into angularity, for now. So read these two slides later. That should have been come like at the end of the chapter. But then again, I'm not into this book too much because it's kind of the way that he structured, like from PowerPoint to everything is just like really difficult. Okay. Of course, if you use a slide as they are, it's pretty good, but then it's not practical. Meaning like we have to print the slides and things like that. It's just messing up with the background pictures and colors. Yeah. All right. So the very first one that we come into is angularity. So angularity is you're like studying a surface. So when you look at the surface, we have center plane, we have median line, and then we have axis. And that surface has a specific angle. Angle with the axis. So this is like your datum plane. And of course, we don't count the 90 or 180 degree. So every angle between the 90 and 180, like this. If you flip, mirror this, turn it to 180 to the other side, you're gonna have also another angle similar to that, but just the direction is different. Of course, some people have a difficulty reading the way that the author wrote it. Don't worry too much about it, especially the international students. Don't worry too much about it. It's just like angularity. We're looking at a surface. You have an axis. Because without that, it's really difficult for us to be able to measure the angle. Because the angle is between, see, the two hands like that. So surface, and then there is sometimes there's another surface, or we have datum plane or datum axis. That's how we do almost all the measurements. So that's what we're talking about. So don't go into, because there's a couple of students who come to me talking about difficulty in reading the text, and don't worry too much about it. You know what angle is. You have studied this geometry since you were little. So angularity, there's a surface, there's an axis. We have we call datum, datum plane or datum axis, because we gotta do the measurement. Because without the measurement, you can never know, the amount of the degrees, or how much degree the two, surfaces or two features have in between them, and that's what we call the angularity. Okay. And of course, we always give a range. The angle, the true angle, can be able to vary, and every time you have a range for for a character, a geometric character to vary. We call that tolerance. Since we're dealing with the angles right now, we call the angularity tolerance. So meaning like the angle can vary in that range. Okay, we will tolerate the angle measurement variation to be in that range. So that's all the steps. Then you got to know two different types of tolerance. Yeah. So one is a geometric tolerance. The other one is the other one is a polar tolerance. So I will just teach you as simple as possible. So you have two tolerance. One is geometric, polar. How are you going to differentiate it? Yeah. So geometric tolerance is limited. Okay, limited. So try to remember that angularity control for your geometry. Tolerance is limited. Parallel lines or planes limited by that limit is defined by parallel lines or planes. For the angularity. And the other one is a polar tolerance for angularity is they are wider. Wider mean like they are wedge shape. Okay, so that's all you need to remember. Another thing that you need to know is like your angularity, right? Every time we take a look at the angularity and the features of your parts, you already know we have range, in which we measure the variation of that angularity, and that range is, we call it in other words, tolerance. Now you know we have two different types of tolerance that is controlling this angularity. You know that geometric is limited by parallel lines of plane, and a polar tolerance is your wedge shape. And the next thing that you've got to know in addition to that, is your constant range. If you have like a parallel zone on your feature, the constant range of that tolerance, is accepted across the entire surface. Right now you can't be able to see this on this slide, but I show you as we go into it. Alright, so let's take a look at angularity and their tolerance. Okay, so the first thing we're going to get into polar. Polar is a wedge shape, and the tolerance zone of the polar tolerance looks like this. See, like a little wedge for this angle, of course. Meaning like this angle can vary in the tolerance, and we call that the polar tolerance. Again, polar tolerance, I said, is wider, meaning like see like how this hand of the angle, the second hand of the angle, this is the measurement plane. So measurement plane for that angularity, and you can see how this is in between that two lines. See that? So the vertex of the angle is here. So it's going to extend out of that vertex right here to from the angle. It's you can be able to see a little wedge, little wedge shape. And every time you see that, and that is your polar, because we call it polar because we're using Cartesian or polar coordinates to dimension, meaning measure, the angles of that. Again, don't go so much into it. You have an angle, and the angle can vary. Why the angle can vary is because the manufacturing technique, manufacturing method, the people who manufacture that, they vary. Okay, so therefore, even though we have a perfect angle that is supposed to be, will not be at that, 30. So if you want 30, somebody make it one part because they have like a different shift, shift 1, shift 2, shift 3, day shift, night shift, all kinds of overnight shift. And the manufacturing of floor is composed of so many different people. So therefore, even though we want 30, that angle 30 can go up and down. And there's variation. So that's so 0 degree and 30 minutes it can vary. So that is what it's saying, and the range is going to be like that. And that range we call it the tolerance zone. And here, since we're measuring by using the polar coordinates, so therefore we call that the polar tolerance. And it looks like a little wedge shape like this because it extends out and away from the vertex of that angle. So now this is the same thing as in here. I don't know why this slide is because he tried to make it like animated. I believe this is a very, very old slide that he is using. So when they prepare the PowerPoint at that time, probably I believe that he doesn't know how to do the animation, yeah. So therefore, it's going the different slide like that, and you're seeing the same thing here. Don't worry about it. All you have to do is just see, there's a little animation which he can put it right in here. But anyway, so I gotta show you the second one, which is like that, and that actually looks like which I have already told you right here. It looks like a little wedge shape here, yeah. That's what we're showing here. Of course, now you can see, because instead of showing you like this, you can see the little field, color blue right here. So you can see that's the angle 30, and it can vary about 30 minutes, like that. Okay, so now we're gonna expand the diagram, and you can see really big, like that. So you can see the vertex right here and the little square box right there very clearly. See that? So now we call that 30 plus or minus 0 degree, 30 minute on and off, from that, from this little angle hand can vary in that range. Okay, so now you can see this angle can go down, in that range. All right. Okay, now we're going to take the polar angle dimension off. So when you take this angularity, angle dimension means the measurement of angle has been taken away. So when you take this thing out, you got this. Okay, there's nothing, just a plain straight inclined surface. Yeah, see that? There is no. If you put the angle tolerance, you can see the angle tolerance like that. If you get rid of it, you're gonna see only that. And look at this, because that datum plane is imaginary. We just stick it there. That's just something that isn't there, or not a part of. It's not a feature of that part. Okay, so this is just imaginary line right there. Then we knew that this angle, measure from this. Of course, this little surface right there, extended imaginally right here. Can make that much of angle right there. So if you take this whole thing out, you're left with that. And that's what I'm seeing here when the Cartesian coordinate dimension tolerances are used. Without the polar angle dimension, then your tolerance is going to be parallel to each other. Meaning like this little I would say yellow line is now representing the range for that surface right here, which is the angle hand, which is this guy right there. So we gotta extend it a little bit in your mind to be able to see the angle very clearly. If you don't have any imaginary lines right there, it's really difficult for you to be able to see the angle. So datum plane and datum axis is very important. Of course, if you deal with the precision parts, then your tolerance got to be smaller. The smaller the tolerance zone is, the more precise your part are going to be manufactured. And of course, why you need your datum reference like this in order for us to dimension the angles to get the angularity, is because if we deal with the precision part, you definitely need the datum reference, or precedence, because without that, you're gonna have an issue in your design, intent and things like that is gonna go crazy. So with that, the datum reference, you can definitely assure your assembly, especially for your precision parts. Okay, now we're gonna see with a little field color blue right here. So you can see the wedge polar tolerance, and we're going to take the angularity right here reference out of it. So now you also have like this little inclined surface in a parallel. See, parallel meaning like the yellow lines are parallel to each other and your surface is in between them, and that we call that a parallel zone, tolerance zone. And this one is a wedge, wedge shaped tolerance zone when we put the reference axis and plane for angularity to dimension the angles. Now we're gonna make this a diagram really big, so exaggerated like that, so you can see the endpoints of that inclined surface. So now you can see the tolerance zone is parallel to each other, so therefore it is called the parallel tolerance zone, polar tolerance zone, because it is a wedge shape. Okay, and telling you the angle reference right here, showing you which is extended from this surface, extended from that surface. So you can see the angle right there very clearly. You can see the tolerance zone very clearly. Remove, the imaginary lines out of it. You're gonna left with a 2 parallel tolerance zone. Okay, all right. Okay, now we're gonna get put symbol for your datum reference. Yeah, so we're gonna stick this datum reference symbol right here on this imaginary line, which is extension of this surface. Yeah, where we want this inclined surface and measure the angle of that, because this is our target tolerance right there, which is angle tolerance, because we're in an angularity geometric characteristics. So we're going to orient with this datum plane right there, the exact angle right here. That's just a parallel zone right there. So we're going to draw this way, put the datum reference right here, which is your plane, and your surface elements, of course. And here, they are parallel to each other here. So let's just go straight like that. So these are the related reference datum reference for these surfaces, two surface elements right there. Exaggerated, your angle, parallel zone, polar tolerance zone, parallel tolerance zone right here. And here's your datum plane right here, and we know that this angle, we want it to be 30, and we know the tolerance, plus or minus right here, given to you for that zone. Then we're going to have a leader, put the leader, and then your control, yes, because it's showing you, this tolerance is going to control that angle right there. So we're going to use our angularity symbol, and then our datum. We have only single datum on this reference plane, which is the relative, related to this surface right there. So we call that the datum reference is D. Of course, we're going to throw in all of this, necessary tolerance material right in here. But right now we're putting it there, so it's okay as well, So that's a 30 degree plus or minus 0 degree 30 minute is going to be the tolerance zone, polar tolerance, controlling that angularity for that two surfaces. One is this surface and the other one is your inclined surface. The angle is between them. You need a reference plane and extension lines like that in order for you to be able to visualize that angle. Okay, now let's get into applications. Okay, so we will go into angle application. We're going to apply the angularity to plane surface, so that's what we call it, a planar surface. Because you have two parallel planes, based on experience, teaching, and the student have a confusion right here. Oh, well, this is seeing like a two, parallel planes like that. So don't worry about it. This is the angle. It looks like the angle when we see the two parallel planes. It's talking about this, zones. See that, So this is what we're talking about. But then, of course, a polar, polar tolerance is a wedge shape and concentrating only this inclined surface. For that one, it's like see that the surface is completely parallel zone, and that's what we're talking about. Even though we do the extension, there is a difference between this and that. So I try to teach you all the time to make sure when you are looking at it what you're seeing. Okay, so don't see this picture and then get the wedge, a wedge shape polar tolerance, because we're not talking about that for the parallel zone. Parallel zones are identified right here, two parallel planes, so it's this one, we're talking about that, and of course it's the same angle anyway, but then when we do this, of course the angularity, and we want to show how the angularity control specifying that zone, we put the leader line. That leader line is not here, that leader line is right there, see, very clearly. I'm going to show you again. If you skip the lecture, I don't know, and of course if you skip the lecture, those students always have confusion between this one and that one, and then they jump to this slide, and then they start reading about this, and then there you go again, two parallel planes. What am I talking about? I don't know which parallel plane we're talking about, and then looking at this thing again, So anyway, so the zone is right here. They're parallel to each other. We're dealing with this surface because you're measuring the angle against the inclined surface, And here is your leader line. I'm telling you about this control. Your control is not targeting the angularity, but showing you the parallel planes, two of them right there. Okay, so that's what it's talking about. Of course, when we think about the angularity, this is just a review. You cannot modify the angularity as it is. because we're controlling the angle of your planar surface. You cannot get the angularity without a surface, yes? And every time we want to measure the angle or dimension the angle, you need the reference to a datum like that, okay? Reference to the datum, that's your datum. Of course, it will always apply regardless of the feature size. Now, some of the international students have an issue trying to understand what is a regardless of the, it is in the name. It doesn't matter what your feature size is. It doesn't matter what the size of your features. These rules apply because we're just concentrating in a geometric character, which is angles, angularity. This angle has nothing to do with the feature because your part is going to be always the part. We're just concentrating the angle for the measurement. Where is the connection? There is nothing. So therefore, this angle geometric characteristic doesn't matter what the size of your feature on your part is. Okay, so we call that regardless of feature size. Okay, it's in the name. Regardless of feature size. And like trying to find where is a regardless of feature size. There is no such thing as regardless of feature size. It's not a part. Okay, it isn't a feature. It's just telling you it doesn't matter what the feature size is. Your angle is we're gonna go with this tolerance. And the way that we measure, we will follow all these rules to get that angularity, to make sure that that angularity is within that little angularity tolerance zone. That's all. Try to make it simple. Science is a very, I don't know what to say, powerful subject to study. We can make it really hard, and also we can make it very easy, okay? So I want you to, practice to make things easy to handle, Then we're going to do our Rule 1 review, So since it is a regardless of feature size, this angularity applies. Your MMC envelope, the size or the form of your MMC envelope is going to be determined by the tolerances, assigned to the size limits. So anyway, don't worry about this. Nobody is going to ask you this either, So because of that, since it doesn't matter what the feature size is, the angularity still holds. So your perfect angular orientation is not required, as a function of your MMC form. This is just telling you in a mathematical way. We always look at the function. Function is nothing but you have a mathematical operation and you put something in and something come out, So we're trying to explain that in a way that size doesn't really matter when we measure the angularity, because angularity is not size, okay? It's just we're measuring how far away from here to here that is, that's all, okay? In angle, of course. So you can be able to perfectly manufacture, or as perfect as possible, to manufacture this part, So if you don't get this angle, it can be like, it will come out D-shaped. Like I can draw that out. Okay, so I can draw this out for you. So if you don't have your angle 30 degree around here, you might, when you manufacture it, it might come out like that, instead of like this. This is, of course, is a very exaggerated drawing, or sometimes it might even come out like this. Okay, so now I see that your inclined surface is not like what it's supposed to be, so material, again, when we talk about the material of the part, we're dealing with the material, See how this angle, angle changes, your material changes. So for this, you have to use a more material. For that, you have to use a smaller material because you made a mistake for that, surface going this way or that way. So your material reduced, material on the part increases. So that's what we're talking about. So in order for you, to get the angle right, we don't really need to do the MMC, okay, envelope. You don't really need to do the perfect angular orientation because your MMC, envelope is determined by your tolerance. So we only have to give the tolerance range in order for us to control, the angularity. So you don't really need to identify the MMC stuff to control the angularity, okay? Because it doesn't really matter what the feature size is. That's all it said, I want you to take it in the way I tell you, and don't go too much into here, and then you can't reproduce when you write it. In the exam, nothing will come out of it. Okay, then let's get into feature control for angularity. So you already knew, I just show you how we point the angularity. So this is your control frame, feature, because it is controlling that feature right here, which is your inclined surface of this part. So here is the part, here is the surface on that part. We want to know the angle of that surface measuring from this plane, reference plane, which is the extension of that surface right there. So we're going to put the datum C, the controlling datum, reference is C, so we put that in a primary datum box right there, which because only a single datum is going to control mean like we're going to measure, from here to there. So from this surface to that surface, you can't study from this, you get a different angle, You can do it, but then some people forget to get the opposite angle of that, because our measurement is, because you can't do the internal part of your part, so you have to get the external angle of your part to get this shape of that part come out right, So you put a leader line and show the surface, hey, I'm concentrating that surface with this control frame is gonna control that surface. Okay, not this surface, not that surface, not that surface, not that surface, not that surface, and not that surface, but this particular surface is controlled by this information. So how am I controlling? I am looking at the angle of that surface with this tolerance, and we want it 45 degree up and down like that. And we're going to measure from this datum plane, which is C, and we stick that symbol right there, with your angle, with this little triangle thing. So since you were dealing with the angle, it's just saying like this is just a routine that we always specify the angle as a basic, basic. And then of course your limits of your sides doesn't really matter, So the limits of the sides cannot be violated. And we only need at least one datum, so right here, that's important. We don't need to do the modifier like LMC or MMC, because it can go, regardless of your feature size. Okay, so when you look at this example, so this one is just telling you this example, we have, of course, your angle is oriented 45 degree from your datum plane, which is your C right here, and your linear, of course, the distance between them is going to be like a 0.5 millimeter away. So again, some people have issue this as where is the 0.5 millimeter away? I don't know. And you have issue understanding what is it this them mean. It means that the parallel planes, right? So that parallel planes is, we're talking about this tolerance zone right here. Yes, so you have a little, remember that the two little yellow lines, right, showing you where this inclined surface is in between that two little yellow line, okay? Anyway, so I drew this two little yellow line right here for you. So we're talking about the parallel planes, which is this two, okay? Because that parallel plane, again, is imaginary for your tolerance zone, So your tolerance zone consists of two parallel planes, which is this guy, and that is 0.5 millimeter, meaning that angle can vary in between them, So it's just like a 0.5 millimeter, so your size is going to come out a little bit or go in a little bit, So that's what it is saying. So this 0.5 is this, right? And that depends on, of course, your angle is from here to here. So that can come like down like that in between that two vertical lines. Okay. All right. I think you should get it by now. All right. I'm gonna erase that. Yes. Let's go to the next slide. Okay. So how are we going to do the interpretation? So all you have to just put that part, on a surface plate. So this is your surface plate. It's happening in the lab, So we're gonna put the part on a surface plate. So when you place the part on the surface plate, then you got that datum plane. Otherwise, you can see it, but you can see only the surface on that part, So when you attach the surface, So when you put the part on this, okay, surface plate, this contact right here, yeah, and that is your datum plane, yeah. So right here we just put, hey, this is the datum plane that we're gonna measure the angle, yeah, from. Of course, for quality, yes, quality control and quality, what you're going to do is you are going to establish that datum plane, and this is where we are going to verify this angle, yeah. So it's very important, yeah, to get this datum plane so that you can do your verification processes, you can do your measurement processes, yeah. If you don't measure, you cannot be able to know the size of the angle. Yeah? In order for you to measure, you have to have a datum plane. Otherwise, it's impossible for you to be able to measure that surface, right? Okay, now we're going to draw these two parallel planes right there, yeah? See that? Which is going to be right here. I already drew that for you. And your tolerance zone, see that? It's in between them, see? Yes? Of course, your angle right here, 45 degree from that surface plane right there, yeah? And surface plane again is created usually, yeah, by your gauge, yeah? So this little two yellow lines, so that's 0.5 millimeter, yeah? And they are parallel, yeah, to each other. And you have, of course, your high points right here in contact with your surface gauge. And because all the elements on that surface, yeah, got to lie between the two right here parallel planes. So this surface right there that we are interested in to measure the angle, yeah. And of course the variation of the angle can go, yeah, from here all the way to here, and that is your tolerance zone, which we put in your control frame regarding that angle. So we're showing a little angle symbol right there with a leader line, so you don't make a mistake where that angle is measured, yeah, from that surface to this, yeah, from this datum plane, and that datum plane is controlled by this, yeah, datum C in this example. All right, and don't forget, yeah, even though we are doing for the angularity, your flatness is also controlled by the same, yeah, tolerance zone, because it is the same surface anyway, yeah. And then of course your tolerance is going to applies, don't forget, your regardless of the size of that feature, yeah, of this part, of course, and then your limits of the size cannot be violated, your rule 1. And your angularity, you always need a datum reference. Without that, it's impossible to do verification or measuring processes. Alright, the next one we'll get into, the first one is on the plane, and the next one is going to be on your axis. So let's take a look at it. Alright, so angularity, we want to measure the angle, yeah, from here to, from this plane all the way to the axis of this. See this little hole right here and this part. So there's a hole right here, it looks like through to me, yeah. So anyways, that's at the angle, yeah, datum reference right here of the surface. We're just going to extend it in our drawing to show that is, of course, your control frame is right here, your datum reference is 8 right here. So we're going to put that in here in our controlling the angle right here, showing you angle symbols right there. And of course your parallel line is going to be around this axis of that hole right there in this part, okay, and that's going to be 0.004, yeah, wide, right? So when you look at it, you should be able to interpret that right away, yeah. And now we're going to draw the little yellow line right there, yeah, showing you your two parallel planes right there, where you can have your axis, yeah, to measure the angle, and your tolerance zone is 0.004. So again, the axis, yeah, it can be anywhere in that range, which is tolerance zone. And that range again is y 0.004, yeah. So that means the 50 degree plus or minus that, yeah. Of course, that zone is acceptable for manufacturing processes. Okay, and then we're going to exaggerate, and here is your datum plane Yeah, and in order for us to see this datum plane, we're going to bring our tool, which is usually a gauge or something. All right, and stick it into there to the high points of that surface on that part. Yeah, and the contact is going to be your datum plane, and we give it a name A. Yeah, and we measure, of course, the angle from that axis to here is about 50, and it can vary about 0.004 plus or minus up and down. Yeah, from here. And we are showing that with a, where is my leader line? And so this is your control frame right there. Yeah, talking about that angle, showing you this tolerance zone where it can vary, this angle can vary, and of course measuring, verifying from that datum plane. Yeah, don't forget your regardless of feature size, your axis got a line between two parallel planes, which is this one, yeah, which is imaginary by the way. And you don't have any other additional tolerance, yeah, for this example. And of course, that specified angle is always your basic dimension. All right. Okay, now we're getting into our example. Yeah, for the application of that method, we're gonna measure the angle, yeah, from the axis. So here is your hole, and here is the axis, and here is your part, yeah. And there's your datum or reference plane, which is a C, and we put it in a control frame like that. The datum reference plane is also determined by a tool, and we call that a gauge or surface gauge. You stick it into the big contact with all the high points on that part, okay? So we can now have our reference plane right there, measure it, and you get like 45 degree, and that can vary 0. In this case is 0.01, right? Between the two parallel lines, which is here, yeah, shown right here. And now we know that it is regardless of feature, your tolerance zone, which is very much a cylindrical tolerance zone in this case, in this example, yeah, and that axis is control, of course, in all direction, yeah, with this. So the zone is about 45 degree, yeah, from the datum plane C. And here, yeah, and sometimes you can go up and down here like that. Sometimes, of course, you can get it in this example, you have a possible feature axis orientation, right, deviate away from that axis right here. But of course, that is outside of that tolerance zone, which is supposed to be that axis gotta stay, but it's outside of it, meaning like that's a very worst case, you know. So that's what it's saying. It can happen like that too, which this part probably will go into defect, yeah, defect group, because you can't use it because it's going to shift the functionality or reliability of that part, yeah. Especially when this part is to be mated with other parts in your assembly. So you're gonna get the state of the art fit issue. You know, fit issue creates incredible amount of fit issues, and people lose jobs because of that too. Okay, then we do the same thing. Our datum in our tolerance zone. In this case, it's 0.01. It's of course a cylindrical tolerance zone. Yeah, because it's going 360 degree around. The parallel tolerance zone and cylindrical, because it's a cylindrical, so we're dealing with the whole thing, yeah, meaning like 360 degree around for that part, not just a single surface. If you got like a parallel, yeah, then you are dealing only a single surface from this view. Be careful, yeah, when you read what kind of tolerance zone, the parallel one or the cylindrical one. You have seen two different examples right now. Of course, this thing is look at the out of that zone, so therefore that's not very good, yeah. Okay, the next example, we're gonna see the angularity geometric tolerance. We're gonna apply that to the feature of size, which is your hole. Okay, so here is the hole right there. We're gonna apply that to our angularity. That's what we want to measure. So we do the same thing. I'll put a gauge right there, stick it into the surface, all the high points of it. So you will be able to see the datum plane right there. We're gonna call it an A. We're gonna put a symbol to identify that plane. We're gonna measure that, and you get like 50, and your measurement got to be from that plane all the way to the center of that hole, which is your axis right there. Yeah, and we're gonna give our specification got to be like 0.008. Okay, that's just showing you the circles right there, so you can see. So this kind of like off, yeah, so that's supposed to be datum A, yeah. So when we deal with the cylindrical, I'm gonna go back one slide. So when we deal with the cylindrical, yes, a tolerance zone like that, your tolerance here is so complicated right here, I don't know why. So anyway, so your tolerance here, 0.008, is not a linear, anymore, because you're dealing with the entire cylinder, and cylinder is a circle, right, with a depth. So therefore, it became the tolerance, value became a diameter. Yeah, so you know that we're talking about a diameter of that tolerance zone, because the tolerance zone geometry, right? The geometry of the tolerance zone is a cylinder. Yeah. So we're dealing with a diameter measure from the axis, all around the tolerance zone limits, which is 0.008. Okay. So be very careful what type of tolerance zone you are getting, right? So if you see the little circle like that, not just a two parallel plane, you know that you're dealing with a 360-degree all around, yeah? So therefore it's got to be a diameter, yeah? All right, the next one, and here is your possible orientation. Of course, it's a little bit bad because it's still inside of the tolerance zone, but then it's out here and then it's out there, yeah? So it's not very good. And your control frame, you have your datum, a datum plane right there, A. Also, you also have a maximum, material condition right there. Because depends on the axis, your material, the amount of the material on that part can change. But we do want to maintain the maximum material. We want maximum material on our part. So you definitely need to have that angle away, within that 0.008, okay, tolerance zone. So, but this example, because this is one of the possible axis orientation, which can definitely mess up the MMC. So your modifier in that control frame right here, feature control frame, your rule number 1, is overridden because we're not following that because of this. So MMC is presented right here in this frame, because you need additional bonus tolerance. So now we're going to put the bonus tolerance, which is backing up this tolerance, which is 0.625 all the way to 0.630. Yeah. So that axis got to be within the tolerances. This, the first tolerance, the second tolerance for that location. Okay. Why do you need the second tolerance? Because of this. Okay. Our rule number 1 is broken, so we need a second tolerance to back up that first tolerance. Okay, now we're going to add the bonus tolerance in this example because we're dealing with the MMC, for the first tolerance. So the bonus tolerance is for your least material, condition, which is in this example. All right, this depends on the specification provided to you, because you're drafting anyway. So that's a 0.013, so 0.013 for the LMC. So your feature size is going to be at the least material, material state, meaning like the size of this feature, the size of this feature is going to be least material condition, meaning this is going to be wider, your hole is wider, it's going to be increased by the amount equal to that departure from that maximum material condition, So your maximum material condition is going to be, let's say, like around here, and then now you have least material condition, so you're going to measure that two difference, and you're going to get by 0.013, okay? But don't worry about how the numbers come to be. Just understand that when you have like an MMC for the first tolerance, then you have a second, bonus tolerance that is going to come amount equal to that departure from the maximum material condition of that hole, okay? And you will be given that. Nobody is going to ask you how to calculate it at all, yes? All right, now we'll get into the angularity application, and we're gonna see our flow chart like we always do, and see how we do the decision. Okay, so our GD&T, geometric dimensioning and tolerance guide, right? So the first one is you're gonna click, what is it? That is his slide. So we will click it and see. Number 1, you're gonna think about if your control is applied, yeah, to the feature of size. So the first thing that you think about in order for us to be able to deal, yeah, with the angularity, because we're in angularity. I'm going to go back one slide here. So we have to make the decision for the correct applications of your angularity for measurement and also for verification, yeah. So let's go into here, and you take a look at your control applied to the feature of size, yes or no. If that is yes, so here, yeah, if that is yes, we're going to see the modifier used in your feature control frame, yes or no. If you have a modifier, your tolerance, yeah, is going to be your refinement of your GD and T, yeah, indirect controls. And if that is yes, we're going to come and look at our datum reference, yeah, your little datum reference in your feature control frame. And your datum reference is yes, then that's an acceptable, yeah, application. So to make it simple, in order for us to do the angularity, deal with the angularity, you're going to take a look at your feature of size, yeah. Then you're going to look at your MMC or LMC. Then you're going to look at, okay, your datum reference, yeah. This is just a geometric control, yeah, dimension and your tolerancing. So just go in that order, okay? Feature of size, look at the modifier in your control frame, of course, look at the tolerance, and then your datum, yeah, reference. All right, you look at the feature of size, your control applied to that. So in this case, since your control, your tolerance is not applied to the feature of size, meaning like it's not applied to the size, it will be applying to the feature, of course, yeah. So because you have only two things going on, one is a feature itself and the other is the size of that feature. So if the size is not the target, then your feature is the target. So that's what we're seeing. Then we're going to look at the modifier, if you have a modifier or not. If you don't have the modifier, we're going to look at the tolerance. If you have your tolerance, we're going to look at the datum reference. When you look at the datum reference and you got it, then it is acceptable, yeah, even though you go with the feature, yeah. All right, then you look at the feature, feature of size, and we are going this way, so that means that we're dealing with a feature. You look at the modifier and you have a modifier, then we can't do it, okay? Why? Because angularity cannot be applied to the feature with the modifier, yeah. That is what the very beginning that we're talking about, how the MMC, yeah, when it comes in and you're dealing with a feature, your rule 1, yeah, is still applied. Okay, then you have your feature of size, you look at it, yes, you look at the modifier, you have the modifier, you look at the tolerance, and you don't have a tolerance, so that's not acceptable for angularity control. And you look at the feature of size, yes, and you look at the modifier, you have it, your tolerance, you have it, and then your datum reference, you don't have the datum reference, so that's not acceptable for controlling the angularity, because you need a datum reference in order for us to measure, yeah. Then you look at the feature size, we're going on feature direction, not the feature of size. You look at the modifier, you don't have the modifier. You look at the tolerance, you don't have the tolerance, so it's not acceptable to control the angularity, because you need like size of your tolerance zone for us to be able to play with the angularity, okay? You look at the feature of size, or feature is going in the feature direction. Modifier, you don't have the modifier. You look at the tolerance, you have the tolerance. You look at the datum, you don't have the datum reference. You need the datum reference to control the angularity, therefore it isn't acceptable, yeah. Then we go again. You look at the feature of size and you're going no, okay, you're going yes. So this is everything that we have done so far, and you're going to follow that flow chart to decide whether to accept or unaccept, right, this way of writing in your feature control frame to decide the angularity, yeah, for the control of the angularity. So I want you to definitely get this. So when you take a look at it, we're dealing nothing but your control frame, okay? So I'm going to go ahead and draw that for you. So you're dealing with like this, okay? So control frame, we want the angularity. So we always look at, number 1, this was your tolerance. I'm going to just write T right here, where the tolerance value is, yeah? So, of course, 1 moment, I'm writing here, yeah? And then, of course, you might have like a Yeah, I'm gonna draw it because I drew it really big, so let's do it like this. Because anyway, so you have your value, yeah, tolerance here, and where you sometimes you're gonna see like am or not, right? In the material condition, which is usually actually have a circle like that, and then of course your datum, yeah. And that's the order of what we're doing. Okay, so you look at for angularity, you look at if we're dealing with the feature or feature of size, just size or the feature. Then you look at the modifier, you know. This can also be L, yeah. And then after that you look at their tolerance, and then sometimes tolerance here, sometimes you also have another tolerance right there. And then your datum, yeah. So that's what we're looking at. Okay, then this is your part. Yeah, after reading, of course, listening to the lecture, you're gonna do your problem 65. And I'll give you some answer right here. Yeah, I'm not gonna go over that anymore. I'm just repeating what I have just lectured you. So make sure you do this. Yeah, you can also choose this. And of course, I only ask you to do three. Yeah, three assignments out of this chapter. Okay. Alright, then we will get into the parallelism definition. What I am going to do is, since we always have a lot of material here in this 201, this is so heavy, I'm going to cut a lecture like a 1 hour each. 2 hours is too long, people can't finish it. Oh my gosh, 1 hour is I think reasonable. It's too heavy for professors, also too heavy for the students. But you only have to do it one time anyway, yeah. And of course, you use your pocketbook, yeah. It's totally recommended because you can't remember everything. You have to go back anyway to look at them. All right, the next one we'll get into parallelism. We know what parallelism is, yeah. So let me go and just draw here. Yeah, this is what we call parallelism. This two planes are parallel to each other, yeah. Mathematical symbol, we just go like two lines, like that. Yeah, like that. So when we deal with the parallelism tolerance, we're just looking at the individual line elements or your entire surface or your center plane, your axis, okay? And again, how much that, of that can vary from your true parallel conditions. True parallel condition means like the perfect, the perfect or the ideal condition. Of course, in real world, in manufacturing, when you're producing these parts, making these parts, in other words, is really difficult to get that, true condition. So therefore, you get something away, more or less from that condition, and we call that the tolerance. And right now, of course, we're looking at the parallelism, where that's a condition where each individual line element, of your surface or all of the elements of the entire surface or a center plane or an axis, they have equal distance, from a datum plane. Again, you need a datum plane in order for us to measure that parallelism. Because without the datum reference, you can't be able to make the verification or measurement processes. All right, then we will get into our the parallelism application. So let's take a look at it. So the first example, we're gonna control the tolerance zone. That tolerance zone is gonna have two perfect parallel planes. Of course, we're talking about something is parallel to the datum plane that we are measuring from. So let's take a look at the very first one. All right, so we have an example. This is your part, and here is our datum reference, which is your D in this case, and we have control frame. We have 1, 2, 3 box. What we're looking at, which is parallelism because of the symbol. Your tolerance, the value of that variance can happen in that range, which is 0.3, and then the datum plane that you're measuring from, which is this guy. Catch that. Of course, we are targeting this, which is also parallel to that datum plane. So let's take a look at it here. Now we're going to draw an exaggerated version of it so you can see all the imperfections on that surface, and that surface parallelism is identified by this datum, which is your datum plane D. And you can see, this surface, of course, it can go up and down in that zone, which is that 0.3, away from each other. So from the reference datum plane D to here, yeah, it's going to be 10. From here to the upper limit is going to be 10.8. Okay. Okay, so I think this is a typo. Yeah, it should be like a 0.3. So either way, you can change either this one to this. Okay, because so from here to here is 10, so this got to be 0.3. Yeah. So anyway, of course now exaggerate I have fixed it here, so you know that whatever that is, yeah, this range, doesn't matter what tolerance value is going to be your surface, yeah, measuring against that datum plane got to be within that zone. Okay, doesn't matter what the value of this is. Don't worry about it. And if you get that big picture, you get it. Okay, we've been doing this with many different types of orientation, so geometric characteristics. So you should be able to know that by now. We deal with the feature of size, so we deal with the feature. Yeah, we've been doing this flow chart several times. Yeah, of course. We also deal with the straightness, yeah, straightness, also flatness when we do the parallelism, yeah, because they are indirectly also controlled, yeah, by the parallelism tolerance, because it's the same surface anyway. So your parallelism, yeah, tolerance got to be less than your size tolerance, and a datum reference is always required, yeah. Anyway, I went and checked this instructor book, okay, and I saw, okay, so why I saw this, okay, I'm gonna change this back to 10.8, okay, it's because the way that like he drew it is kind of like a misleading, right? He is right here just trying to show you the size, all right? He shouldn't be putting this, okay, like that when we teach you for the very first time, yeah, because you can get a confusion with that, which I already did. So anyway, so this is just meant for the size, right? And that is for the parallelism. So therefore, this is supposed to be right here in the two ways, okay? So that's going to be 0.8 right there, you know, and here is going to be 0.3, okay? So that's, and I don't know why he didn't, yes, write it down here. So only here, yeah, when I was doing this slide, I found out, okay? So don't worry about it, because your parallelism tolerance got to be always less, which is like a 0.3, yeah? And then your size tolerance, yeah? I wouldn't put 0.8 here in there. I would just go with 0.3, highlighting, yeah, parallelism, and ignore the size tolerance for now. But I think because he wanted to point this out, so he just put it, yeah, both together in here. So the reason for this is 10.8 and 10, and the reason for this parallel 0.3 is just that he want to point out this, okay, which I didn't catch it from the previous slide. And yeah, of course, your MMC and the rule 1 goes the same way as you know, our angularity, okay. Okay, then we get into tangency, yeah. So tangency parallelism, we're going to establish by bringing a gauge. We always bring a gauge for us to be able to see the datum, you know, plane. Of course, give it to that gauge to a surface that of interest that we want to measure. This the tangency parallelism, and then you're going to use that point of contact to establish that plane. And we do that all the time, so you should be able to get that by now, yeah. And we will go in each one of them written here, yeah, by using this example. So here's our part, and here's our datum plane right there, yeah. Now let's go into this upper limit, okay, and then your lower limit, which is showing you the zone, yeah, of this tolerance, which is 0.2, okay. And we go back to the first slide, and you see this is for the size of that, yeah, part, and this is for your parallelism for that surface, yeah. So we have different, and 0.2 for the zone, which is here, yeah, and then we have, of course, the size is going to be different. The zone's got to be always less than your size, yeah. Now we go into here. Now it's the exaggerated surface that you can see that's not that very parallel, yeah. Your tangency parallelism is kind of very, very bad here for this example, but still within the zone, so it is, yeah, acceptable. And we have our symbol for parallelism, we have our parallelism zone, tolerance zone, 0.2. And then this is just showing you the tangency, and then of course that's your datum plane. Of course, there's a little blue line. It's just showing you this surface right there. Of course, it is like inside. Most of them are inside of the tolerance zone for parallelism, but then here is a little bit off right there. And that can happen, of course, in real life a lot. For tangent or tangency parallelism, your surface flatness is not controlled by that. It's only for parallelism. Alright, then we'll get into another example here. And here we're looking at this, your axis parallelism, because we're looking at this axis. And now we change the view right there. So that's where you want to look at that axis, got to be parallel to your datum, C. So you're looking from this side, of that part. So you can see this, this is your front view. So your surface, is actually right here, So we are measuring this and that for parallelism in that tolerance zone, backed by another one right here. So datum, the exaggerated surface right there, and we're measuring, with this axis for that datum plane C, your sides, and then your tolerance zone, which is this guy, and that's going to be line 0.2. Yes. And when you look very, very carefully, you can see like two different zone size, and then also the parallelism tolerance. It's just right there. And then of course, now we can see this axis, is definitely in this 0.2, parallel planes. In which, again, these planes are parallel to this measurement datum plane, measurement reference and datum plane. Your straightness, which is of your feature axis, which is this guy right there, is also controlled within your parallelism or tolerance zone. We don't have any modifiers because when you look at the control frame, there's no feature control frame. The feature being controlled is here. We don't see the modifier right in there. And it applies a no modifier, meaning it is, applies to the regardless of the size, feature size. Applications, another one. We're going to see our cylindrical tolerance zone, same thing, this part. Your control frame, this is just your size, and here is your tolerance zone. And now we'll identify that with the diameter, So I go back here when we were recording this, slide. There's no. Yes, I for trying to put this because it's like all the objects are like layered, and it's really difficult to take that out. I managed to take that out anyway. So here, when we were dealing with the cylindrical tolerance zone, you were supposed to have a symbol of diameter right here. I just want to point that out. Now I can successfully put that in. So now we come back here, and that is what I want to point out. So here's a cylindrical tolerance zone with your maximum material condition here, and we are dealing with this tolerance zone. We're referencing the entire 360-degree around. So you're dealing with the diameter for that. Okay, this is all I need to point out for this. Okay, and we have our control zone right here. Which is tolerance control zone, diameter 0.2, got to be in that range, and we want the maximum material, meaning like this material of that part got to be max, so therefore this tolerance got to be 0.2 around there, and we're looking at the parallelism of that, two little cylinders, and then of course our reference plane right here, is your E, which is this plane right there. Okay. Of course, with the front view, it's really difficult for you to be able to see it, but on the side view, we can be able to see the two holes right there and two axes right there, and your datum axis established with your gauges right there, of course, and your control frame is right here controlling that. And we go back here, and now we put our zone right there, so you can be able to see and showing you this little circle right there to point out that hey, we're dealing with the diameter, yeah, tolerance for this, yeah, and parallelism is right here that we try to measure, yeah, for verification processes or dimensioning processes, whatever like you want to do, but definitely we want to get the distance, yeah, from here to here, and we call that the parallelism. Of course, you're dealing with a cylindrical zone, and sometimes you're gonna get variation in that zone like this, yeah. Some of the variations are good, some of the variations are bad, but try to make it as possible as you can to have your x's in that yes range. Okay. Of course, that zone got to is bound to be parallel to your datum axis, yeah. And within that location, tolerance, and it's got to go throughout that part, okay? And here we show you again, you have your x's, and you also have the tolerance zone right there for LMC, and this one is your MMC, yeah? And this one is your LMC. You're going to have a little bit of a difficulty to identify LMC and MMC, yeah? All you have to understand the least material, I mean here, see the section lines right there? So that least material, meaning like how much of the part is left because of that hole, yeah? And if it is max, this material got to be more, so the hole size is smaller, least material, so the hole size is bigger, yeah? And of course, depends on the hole size, your axis varies, yeah? Whatever that is, you still need to maintain these two axes got to be parallel to each other, meaning like doesn't try to avoid as much as you can when you manufacture or draw the design, not to vary so much, yeah, from that zone. Try to keep it within that zone, okay? And make sure you understand that your tolerance zone is not identified as a cylindrical tolerance zone, not just a regular parallel one. So parallelism tolerance between here and there, is applied to your size, yeah, feature size. You have modifier, and your rule one is overridden, and you need to do your bonus tolerance, yeah. We can also control the straightness, yeah, with the same there's a control frame. All right, then parallelism implications. Let's see our flow chart, how to decide. We're gonna start, yeah. So if you go with the original blue, yeah, blue's like USC, but then I got bleached, so some of the students can't be able to print them, yeah. Alright, so now we see our control is of parallelism. I'm gonna see and decide whether that's a feature or feature size. For feature size, we take a look at your modifier. Then we're gonna take a look at tolerance. Then we're gonna take a look at datum. If you get all of them, if that's acceptable. You don't have the control for feature size, then it must be feature. Look at the modifier. You don't have modifier, you look at the tolerance. You have tolerance, okay, and then you look at the datum. You have it, so that's acceptable, yeah, even though you're not dealing with the feature size. You look at the feature size of feature, it is feature size. Look at the modifier, you don't have the modifier. Then you're gonna, since you don't have the modifier, we don't have to go into tolerance, it's not acceptable, yeah? Because every time you deal with a feature, to control the parallelism of the feature, you have to have a modifier, yeah? And when you have the modifier, we can't control the parallelism, okay? All right, now we look at the feature size of feature. You look at the modifier and you look at the tolerance. You don't have the tolerance, so that's not acceptable to control the parallelism, yeah? You look at the feature size of feature, you look at the modifier, you look at the tolerance, you have a datum, and you don't have the datum, so therefore it is not acceptable. You look at the feature or feature size, it is feature this time. Look at the modifier, you don't have the modifier, so that's okay.
Catch that.
And you look at the tolerance, and you don't have the tolerance, so therefore it's not acceptable to control parallelism, yeah? And if you do have the tolerance and you look at the datums reference, if you don't have the datum reference, it's not acceptable. Now we look at the feature size of feature. It is a feature, okay? If that's the feature size, go this way. If that's a feature, go this way. Yeah. And of course, we have many different tests right there to look at. Do we have the modifier? Do we have the tolerance? Do we have the datum reference plane for us to be able to decide an acceptable. And this is our flowchart. It's a little bit off, but don't worry about it. This is just trying to bleach the background color out of it for you, yeah, so you can print. And here's the exercise, and that's the problem number 66 in your book, and make sure you do this. And I give you some answer so you can be able to take a look at it when you study, yeah. Make sure you study. Studying is not copying. Studying is studying, yeah, reading, and then try to reproduce that you actually understand that, yeah. So some student, you really lazy and they will just copy the answer and turn in the assignment, but they're not actually studying, so you will face a difficulty in your exam or tests, yeah. But then some students just want to do the assignment and to get the passing grade to finish a class. So in that case, of course, you can only do the minimum amount of it's studying, and you don't care about failing the test or not. It's okay. Yeah. Also, it depends on what you want to do anyway. But we encourage you to actually study, so you can be able to do your job. Okay. Then we'll get into the last one, which is your perpendicularity. Yes. So perpendicularity, we're dealing with how a surface is perpendicular, to another one, and you will of course measure by using our datum reference, to get that measurement. So anyway, so all that we write here for the application, we're going to go with the example so you can be able to see. Mostly we're doing the same thing, and everything that we do is in the control, a feature control frame. Okay, so here we go, and this is our feature control frame right here. We're dealing with we'll control the perpendicularity by using this datum plane A. Our tolerance is given here, and this is just a size, yeah. All right. Now we're gonna draw it a little bit bigger. We're gonna bring our surface gauge, yeah. Then identify this plane, datum plane, from which we're gonna measure, this perpendicularity. Perpendiculars usually make a 90-degree angles, yeah. We do the same thing here. We're gonna draw our zone. You have a size, and you have also the perpendicularity tolerance zone, which is like 0.005 far away. And of course, here's the angle I'm mentioning previously, the 90-degree. This surface and that surface is going to make, okay? All right. Then you give it another part, yeah? And right now, we're going to measure the perpendicularity by using, a different feature. And here we're going to use the axis of that, and our plane is identified with this surface gauge. Yeah, so right here is our axis, and your angle got to be 90. Yeah, with this datum plane. Our feature control frame is telling you we're looking at the perpendicular here. Perpendicularity here, 0.5 is our perpendicularity tolerance, and we are using the datum plane A. Yeah, for it. And of course, we're measuring the axis this time. Now I'm going to go faster, because you have already done two. One is the very first one, angle, and the other one is parallelism. And we're using the same method, so perpendicularity should go faster. Another part, do the same thing. We have two, is identifying your first, which is your tolerance, perpendicularity, datum plane is C. Since the datum planes were giving different view, try to understand that you are looking at that, yes. because you can't see this one from that side, because we're like looking at from this side, yeah. So you will see only the block right here. So this is that, yeah. Okay. Axis, yeah. Bring it in 90-degree. Your datum. See right here, and it's got to be in that range, which is 0.3. Okay, pretty easy. Next one. Zone right here, 0.3, okay, showing you either this or that, because you have two of them, okay, and that's just the size, and that's the zone. And we're gonna go to the next one. Your surface gauge, you cut it, and you can see the section lines right there, so getting into it. Your angle, your datum plane simulators right here, and nothing really changed, yeah, these are about the same thing. But the only thing is like we're dealing with a cylindrical feature. Yeah? Then your RFS, regardless of its feature size. Meaning like we're getting into the feature stuff, yeah? Because you have only two things anyway, one is size and the other one is feature, and we can go both ways. And you have already seen two different flow charts, you know? Perpendicularity, your tolerance zone, we're gonna look at the entire diameter. So your descriptor is going to be right here, diameter symbol. And we put it in a feature control frame, yeah? Your datum, plane is right here. And we're gonna show everything. The same thing. We're going to draw our zone right there so you can see it. Yeah. Your gauge is a little bit different because our perpendicularity is dealing with this axis and that, right? And your angle. Yeah. So here we can draw the datum with this little yellow line right there. Take some time to take a look at these things, okay? And of course, we're going to put our gauge because our perpendicularity is we're dealing with this. Yeah. So these are just variable gauges, and put that cylinder part into here. Again, these are very exaggerated drawing, yeah, to be able to see this datum plane right there. How we establish the datum contact. Your three high points, and here is your cylinder zone. Cylindrical zone, which is a diameter of 1.3 for the entire thing, 360-degree around, and it's got your axis got a line within that zone, yeah, to be acceptable for manufacturing. Of course, we go in, yeah, and show you how they can vary and sometimes come out for the worst case scenario like that. Yeah? And we talk about the regardless of feature, yeah. And also another thing is the feature of size, yeah. If your control, this control is associated with a feature of size, and then your rule 1 is going to be overridden, otherwise follow, yeah. And what is a rule 1 and what is a regardless of feature? You will study the flow chart, yeah, two different ways going where we make the decision yes or no by looking at this perpendicular is, are we going to apply that to feature of size or feature, yeah? And then you decide for the tolerance, you decide for the maximum material condition or least material condition, yeah, one of them, and then your tolerance, and then your datum one by one, yeah? You have to have these things in order for us to control the perpendicularity, yes? And also what we're talking about here. This is the same part that we use, but this time we're dealing with the maximum material condition, yeah, because of this. Go back to here. Here, yeah. So we're dealing with the regardless of feature size. And we're going to go in each one, yeah. Do the same thing with the gauges. And you have this, which is your gauge diameter. And that's going to be equal to your 12.2 millimeter, yeah, in this example. because this is 0.2, so that's 0.12.2, okay, for this diameter. But that's the size, yeah, diameter of this size, 11.4, and all the way to 12.0, and then your tolerances in between them. And we show our angle. This is our axis, and this is our datum A. So the angle is right here. I've got these fixed gauge because we are verifying that perpendicularity between this plane and that axis. Now we're dealing with the feature, and that feature is being controlled, and we have maximum material condition here. I'll try to fix this easier for you to read. That's what's kind of like messed up in the slides. All right. Okay, so here you have your max material condition, and we're dealing with this axis and then that plane. And in this case, we are overriding the rule 1, yeah? So every time you see the MMC, know that we're overriding the rule 1, and your control is on the feature size, okay? And when we do that, you need a bonus tolerance, okay? So repeat it again and again, the same thing. Apply to, of course, a different example. And here, your least material condition, meaning like the distance now between that two is going to be 11.4 all the way to 12. And that's what is showing you right here. If that's the least material, meaning like we want, yeah, the material of the part to be the least. So therefore the distance is at its max, yeah. For maximum material condition, the distance is least. Now we come into a different view. This one is showing you, yeah, the perpendicularity between this datum plane A and then this axis. Your diameter, we're going to add 0.2 for the tolerance, yeah, with the upper limit, because we're dealing with the MMC. And the geometric tolerance is 0.2. I'm just showing you that we're adding it, yeah. So therefore, you're gonna get the acceptable, yeah, variations on. Okay. We can see here, yeah, where the gauge is, and then your part is like that, and we're concentrating this, yeah, zone right there, so you can see better. Of course, we'll get into another part, yeah. If you need a perfect orientation with your MMC, your max condition, you can specify that by using the 0, yeah, 0, which is this little guy right there, this feature control frame right there. So that's a tolerance value. And we do that when we want to design, yeah, a perfect orientation without any kind of deviation. Meaning like this is really strict, you know? Meaning like we don't tolerate anything, it's got to be so perfect. Your data, okay? Here, right there. Okay. I don't know why this thing is so big, it's supposed to be smaller. So anyway, it's a little bit difficult to fix this thing. Yeah, okay, I'll fix it. So every time I have to deal with these slides, I got a headache. So anyway, so here, yeah, so this control feature frame is going to control that feature right here. And it's, of course, it's necessary to limit that bonus, you know, tolerance effect to that maximum limit. So what's basically saying is like we can go with just this perfect, you know, 0.0 tolerance because it's so unrealistic. Of course, you still need, you know, a bonus tolerance, and we are going to deal with that, and we're going to add that in. Yeah. So here is your additional, you know, cell for your feature control frame to specify your maximum tolerance, diameter, which is permitted to control that perpendicular right here. So this is what they're saying right there. Well, I do my best, but it's kind of off. But you know that is got to be right here, which is additional cell to our regular, which is like this, because we're adding something to compensate that perfect 0.0 tolerance. So you kind of get it, and this is your datum reference is now pushed all the way back because we're putting a diameter 0.4 max for it to departure from your max. Okay, and I don't know why the whole frame here in the drawing is so messed up. This can't even like control. I don't know, it's just like he make it really difficult for any of the slide to change, and it's just so weird. Like this, I don't know why some of the people do like that. You have to give some flexibility and control for the teaching, or other user who use this. Oh, I can't get it. Use this to be able to use their slate. Well, we'll kind of get a little bit better. Then I can't fix like every single one of the slide like that. Okay, so I try all my best to fix it, and now it's done. Well, that's the best we can do for now. So anyway, you kind of get it when you write it. Pay attention when you identify. Also pay attention to that. Okay. And then we'll get into perpendicularity to put into the first example here. And here, of course, here, make sure that the box got to be aligned with that. It is difficult to manage here in the slide. Okay, so we have MMC, which is like 8.6 diameter, your stud size diameter, here, written there for you. Right there is your size, from going from like 8.0 to 8.6 in diameter of that little hole right there. And here is our control frame right here, and we are dealing with that, and we have 0.0 for the perfect, so therefore we have additional tolerance to control that. And here we're dealing with the perpendicularity, which is this angle between that axis and then this data reference, which is your A right here, and this two front and side view. Now we'll get into each one of them. Your allowable tolerance starting from 0, and it's going to keep going all the way to 0.4. So we go 0.1, 0.2, 0.3, and then go all the way to 0.4. Okay? So at 0.4, we're going to stop. So every time we increase, you go from 8.6, so going all the way down to 5, 4, 3, 2, 1, and then 0. Okay? So that 0 is your maximum, which is 0.4. So this is just showing you how, that is a reach departure from that MMC. You can see the MMC go all the way towards the LMC. And you go about 1, 2, 3, 4, okay? And don't go beyond 4 because your max is 4, so you don't count it like to 0.5. When it goes from approach from 8.2 to 8.1, you still count the same, 0.4. It can't go anything more than that. The same thing is true for when you approach 8.0, where you get to the least material condition. Your max and your least is right there, Okay. So that's how you fill up your tolerance allowance when you deal with 0.0 tolerance zone. You can go all the way to max. You're going to increase each unit coming out from the max, which is this upper limit, towards your lower limit, which is your 8.0 in this example. Okay, all right. And then we will get into our surface line element control. So the line, your perpendicular is going to apply to a line element instead of your axis. So here we go. And here is your perpendicularity, your tolerance, and then your datum. And we're dealing with this datum axis, established by that datum reference. Of course, your perpendicularity can be able to vary within that zone, and that zone is 0.003. we're repeating the same thing. So now I go a little bit faster. So I think you are pretty okay, yeah, to spot your drawing. So here's your reference, your tolerance, your reference here. And of course, this is your, we call it just element. It's just showing you, yeah, your position in where your surface, surface is, and from which reference, plane that we measuring this angle. Yeah. Now, as you know that we're measuring this axis and that surface, so your tolerance for the perpendicular lies right here. Yeah, and it's pretty wide. Of course, it's 0.003, but it's still acceptable. Yeah. Okay. Then, since we're dealing with a line element on the surface, we gotta identify what that is, which is this one. Yeah. So when you look at this part, and you can be able to see this, from a different view, and you can be able to get this. So that's your top, and then this is your front. Yeah. So that's where this, see the hole. So the cylinder, and here is your axis. Yeah. Then here is our surface right there, and this, look at that, is your datum, plane right there where we measure this angle 90 degree. Okay. Of course, our control frame is right here, and this is your line element. Okay. And our parallel lines in your exaggerated diagram, we can see it. Yeah. And this is your 0.4, because it's set it so here in your control frame right there. Yeah. We do the same thing. Yeah. Your gauge, your surface, your high points, at least you need 3. Yeah. Why? Because your primary data. Yeah. Don't forget these things, please. Don't want to repeat it again and again. Of course, to be acceptable, your each line element meaning like just a control. Yeah. They are always connected. Here, in this case, you have 2 parallel lines to see this. We always refer to this, your tolerance zone, which is this guy anyway. That's all we're talking about. Even if you're studying the same thing with different terms, yeah. Just make sure that whatever you're measuring got to be in that tolerance frame, because this control it, right? This one completely controls it, and that's why the name is a feature control frame. This frame control that feature. Yeah. Of course, since we are drawing this view in this example, which is this guy, yeah. Where is I'm trying to, oh, here, yeah. So it's mentioned here as well. So since we are dealing with this view, it's set here. See, the control applies to the surface line elements only in the view where it is specified. Yeah. So if you change the view, it's a different thing. Of course, here we can see the front. Yeah. When you do the front view, then we can see it, but that is only for that. Okay, which is this guy right there. And we deal with these line elements on that view. Okay. Okay. Then let's go into your regardless of feature size, the same thing. Your perpendicular is going to control your individual line elements on that surface as specified here. Your rule 1 again. We take a look at your max and we don't have it. So rule 1 is in effect. If you see the max right here, rule 1 is overridden. You should get it by now. Yeah. We've been doing this again and again. So your size envelope, you can't violate it because we don't have MMC to worry about because we're dealing with the rule 1 here. Yeah. So what does it mean? The same thing. Your object got to have a perfect form at the maximum material condition. And we don't have a size tolerance here. Yeah. So therefore, just go with your max is going to depends on this tolerance specification. Okay, we go into our flow chart for decision making for the perpendicular control. So we're going to take a look at first is your feature size, yes or no. If we're dealing with the feature size, we'll look at the modifier, yes or no. If we have a modifier, that's your first example, then we will look at the tolerance. If you have a tolerance, we will look at the data that is acceptable. And if that's not the feature of size, you're dealing with the feature, you will look at the modifier. If you don't have it, you look at the tolerance. Okay, if you have the tolerance, you look at the datum. If you have the datum, it is acceptable. Yeah, the only thing is right here and right here differences. And then feature of size, you look at it, you look at the modifier, you don't have it. If you don't have the modifier, we can do anything about it. It's unacceptable because you're dealing with a feature of size. You need, okay, the modifier to keep going.